this is question 2 from the 2015 MAT. So we start off by expanding and simplifying this thing. Right, let's write it out with, I'll do it on 2 lines, there's a lot of it, but I can squeeze things up here, I think. So a n plus 1, I'll do all the a's first, plus a n b plus a n minus 1 b squared plus dot 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 plus a squared b n minus 1 plus a b to the n. Right, now let's do the b's. Keep the a's at the beginning though of each term. So minus a n b minus a n minus 1 b squared minus dot 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 minus a b to the n minus b to the n plus 1. Right, so I'm assuming we get lots of things cancel. Yeah, that cancels with that, that cancels with that, that cancels with that, that would have cancelled with something in between. We're just going to be left with the first and the last terms, aren't we? So a n plus 1 minus b n plus 1. Okie dokie. The second part, the prime number 3 has the properties 1 less than a square number. Are there any other prime numbers with this property? Justify your answer. Right, is this coming off of the previous part? Or we're just doing something else? We want a 1 less than a square number. So we're saying that x squared minus 1 is prime for for integer x. So we have to have that. And it's going to be a positive integer x. So we've got that. Are there any other prime numbers? Is that going to come out of this first thing? I mean, normally, if we hadn't have done the first part, I'll be thinking, well, that's the difference of 2 squares, x plus 1, x minus 1. I just can't immediately see how this is fitting with the previous bit of the question. But still, let's go with this bit and see what happens. So x plus 1, x minus 1, we want that to be prime. So one of these is going to have to be 1 then, which means that has to be 1. It can't be the other bit. So we need to have x is equal to 2. That's got to be equal to 1. So it only works for x is equal to 2. So only works or produces a prime for x equals 2. Oh, okay, so usually they follow on, but that one sort of threw me a little bit there, but that's okay. Find all the prime numbers that are 1 more than a cube number. Right, so, we're doing a pretty similar thing then, aren't we? So we're saying now that, let's carry on over this side, 1 more than a cube number. So x cubed plus 1 is prime. So x cubed plus 1, that factorizes, doesn't it? Because we're going to have x plus 1. Obviously, x minus 1 is a factor. That's why you can see it factorizes. So we'd have to have an x squared. We'd have to have a plus 1. And then we'd have to have a minus x. So we've got one of these things has to be 1. And it's not going to be x plus 1. Because x has to be at least 1. So we're going to have then that this thing equals 1. So we've got x squared minus x plus 1 equals 1. So x minus 1 equals 0. So we've got that x is equal to 1, or it's equal to 0, but we don't want that. So x is equal to 1, which is just saying that we've got 1 cubed plus 1 is prime, 2 is prime. And it's 1 more than a cube. Okay, find all prime numbers that are 1 more than a cube. So that's going to be 2 is the only prime number that's 1 more than a cube. Okay, this is going okay. Part 4, 3 to the power of 2015 minus 2 to the power of 2015 is a prime number. Explain your reasoning carefully. Right, this has got to be going back to the first part of the question then. So we've got that. So what is that telling us then? We've got that and we've got this. So these things are the same. So we've got a n plus 1. So we could say, okay, the n is 2014, which means we've got a minus b. So that would be 3 minus 2, right? That gives us a prime. It gives us a 1, I mean. And then we're going to have a to the n. So a is 3. Let's just put that down. B is 2. So we'd have 3 to the 2014. Okay, that doesn't sound very nice. And then 3 2013 times 2 plus 3 to the 2012 times 2 plus keep on going, plus where we get, I'll do the last two terms, so that'd be 3 times 2 to the 2013 plus 2 to the 2014. Is that a prime number? Explain your reasoning carefully. Is that prime? I mean, we've got the 1, so this would have to be, can we show that this has got some kind of factor? I mean, they've all got 3's and 2's in, but then we've got the first term and the last term, and that's going to be odd, and that's not going to be a multiple of 3. So how am I going to pull a factor out of that? Well, I'm not, am I? Right, so that hasn't helped at all. So, but I got a number that maybe I could engineer that to not be equal to 1. If that wasn't equal to 1, then we'd have two numbers multiplied together, because this is just getting bigger. The second bracket, we're just adding things together. So that can't be equal to 1. So let's try and make the first bracket not equal to 1. So how am I going to make the first bracket not equal to 1? Let's go back to what we're looking at here. So this would mean putting in numbers that aren't 1 apart. So we can't have A and B. We'd have to have, we'd have to split this power. Have to split the power. So 2015, so it is a multiple of 5. So that will be, well, divide by 10 and then double it. So we're going to have 403. So let's write this then as, right, so let's go with this. I'm saying that 3 to the 2015 minus 2 to the 2015 is equal to 3 to the, well, I could go either way. Do I want to, I probably want a higher power here, don't I? And then the lower power on the outside, but well, it doesn't matter. But that's 5 times 403 is 2015 minus 2 to the 403 to the 5. So we could have that instead and then say, okay, well, that is then, so now A is 3 to the 403, that's 2 to the 403, and N is then going to be 4. So this is what we're doing this time. So we're saying we've got, well, let's get this right. So we're doing A minus B, so 3 to the 403 minus 2 to the 403. So that's certainly not equal to 1. And then we're going to be multiplying by A to the N. So, well, big numbers. I mean, you can write all of this out, but it doesn't really matter what you're going to get there. You're going to get 3 to the 403 and then to the power of 4, and then plus all of these terms in between, all the way through to a 2 to the 403 to the power of 4. So we've got something that is greater than 1 multiplied by something else that's greater than 1. So it is not a prime. Now we've got these two integers, that an integer greater than 1 multiplied by an integer greater than 1. So it can't be a prime number. Okay, that was tricky. We say, yeah, it kind of leads you into doing this unfruitful approach in the first place, and then having to unpick it. So yeah, that was a tough one. Is there a positive integer k for which k cubed plus 2k squared plus 2k plus 1 is a cube number? Explain your reasoning carefully. Right, so positive integer k. So we've definitely got that. Right, where am I going to start with this then? So we've got k cubed plus 2k squared plus 2k plus 1. And that has to equal some other cubed. So say n cubed. So is that ever going to be the case for, so we've clearly got n is a positive integer, k is a positive integer. Then what does that mean? But then we've got a cube sitting here. So that could work. Because I don't know, having this n cubed there, we're not going to be able to factorize anything here. It's not like we can say, yeah, let's pull out a k plus 1 out of this left-hand side. I don't really see that's going to help very much. But we do have a cube plus something is equal to another cube. So that is one thing. So we're saying that we've got a cube, we've added some stuff, and then we've got another cube. Start with k, move to n. So what would this next cube have to be? It would be further up. I mean, what if we said that this was equal to then k plus j all cubed? And then we don't have to worry about the n. I know we've still got an unknown of j, but so we're saying all of this stuff then on the left-hand side would have to be equal to, well, this is k cubed plus 3jk squared plus 3j squared k plus j cubed. Right, so j has to be an integer as well. So where j is an integer greater than 0. So, but it can't be in order for these to match up. Yeah, so these just can't match up. It just can't, it's just not possible. So we can't do this. This is always going to be bigger than this because we've got 3's rather than 2's. So even if, I don't know, what do I just, is that enough? Do I just say that? Or do I actually put in j is equal to 1? And actually, yeah, it's an easier way of describing it if you put in j is equal to 1. Because what we're saying then is that k cubed is less than k cubed plus 2k squared plus 2k plus 1. But then that is less than k plus 1 cubed. As in, if we put in j is equal to 1, then we get something bigger than that term. So we're between two consecutive cubes. So what we need to say is that that term is between two consecutive cubes. Therefore, is not a cube. Right, yeah, that was a sneaky one. In fact, the last two parts were really a lot of problem solving on those last two bits because it was in no way obvious where to go on those, as in the starting point didn't actually lead, the obvious starting point didn't lead to the solution. You know, we had it here with this thing of ending up with a 3 minus 2, didn't lead us to the solution. The same thing here of having that n cubed bit in there didn't immediately lead to the solution, but there was a way of engineering it to become the solution that we want. So yeah, that was, I would say that was a pretty difficult question all round. Okay, the first part was fine, but yeah, all of the others, that's a tough question too, I would say. Question 2 is often one of the tough ones, and this one, I think, for me, I would say was one of the tougher ones. But there we go, another one down in 2015.